All right, so we're talking about forces. All right, so in the case here, if you have your vocabulary sheet, all right, we know that a force is a push or a pull. All right, one thing exerts onto another. So the main idea here is forces are pushes or pulls. Okay, and so obviously, there's somebody at my door. Did they knock?
Yeah.
I didn't hear it. I'm busy talking. So, for right now, for me to open that door, I had to pull on the door. That was me applying a force. Then for me to close that door, I had to push the door back. That was a force, all right? In order for basically objects to move, you have to apply a force. But the one thing we want to make sure we understand today is this. In nature, all right, you have a battle between forces at all times. Okay? Now, there are different types of forces. For example, you have the force of gravity, which is what causes things on Earth to drop or fall. All right? But you also have the force of friction, which is what allows things to slow down or stop. So, at all times, whenever we have forces that are being around or being applied, that those forces are always in combat with something else, another force. There's always a competition between the two. For example, you are sitting in a chair, okay? You are sitting in a chair, but you are not falling through the chair, meaning you're not breaking the chair. The chair is applying a force upward onto your body, which is why you're sitting still, all right? But at the same time, your body is applying a force going downwards. So you have a force going up, you have a force going down, all right? And so because of that, you have those two forces that are going in opposite directions. You have a battle of going up versus going down, okay? Now, obviously, if I were to ask you the question, if the chair is applying a force up onto you and your body is applying a force down onto the chair, if that's the battle, right now, who do you think is winning?
The chair.
The chair. All right? Because if the chair were losing, what would you be doing? You'd be sitting on the floor because you'd be breaking through the chair, right? The chair would fall apart. All right? And so that's what we're trying to get you to understand, is that a force is a push or a pull, but in nature, forces are always going against one another. All right? Sometimes those forces are upward and downward forces, like in the case of gravity. All right? But sometimes those forces are the forces of friction, like between your tires and the road whenever you're trying to stop. Because you can slam the brakes, but if you're driving on ice, is your car going to stop? No. So friction does have a purpose, all right? And that is a force that is to slow down a car. But what we want to understand so far today, though, are going to be these two words. Today's battle, today's idea that we want to make sure we understand, is the idea of balanced versus net forces. Okay? That's what we want to make sure we understand here, is the issue of balanced forces versus net forces. Okay? Now, what I'm going to do here, though, is I'm going to throw another word over here underneath net. Okay? A net force, for our simple purposes today, is what we call an unbalanced force. So anytime you see the word net force, just realize they're not equal. And because they're not equal, there's going to be a winner. Okay? But if you're balanced, right? If you're balanced, that means you're equal. So if I were to say, if I said Barney has $10, Jasmine has $10, their money is equal, correct? So who's richer? Neither. Right? That's kind of how it is. Well, that's the way we talk about it. When you have balanced forces, you don't have a winner. Okay? When you have unbalanced forces, you have a winner. So what we need to see here, though, is the issue of what does balanced and unbalanced, or balanced and net forces, kind of look like. And that's what I'm going to give you the diagram for. The purpose of the diagram is to help you understand the difference between balanced and unbalanced. So I need to erase this to give me some room. Are we good to erase this? Yes? All right. Then what we're going to do first is we're going to do a side-by-side. So in your notebook, go ahead and just draw a little line that separates left half from right half. Okay? Doesn't have to be the rest of the sheet. but just a little section there because I want to have it a side by side. So over here on this side, we're going to put balanced forces. All right, and then over here on this side, we're going to put net forces, all right, which is again unbalanced. And then I got my line. Okay, so here's my diagram. All right, we're going to pretend that we have this box. So we're going to have a floor, the ground, and then we're going to draw a box. Okay, and I'm going to do the same thing on the other side. Okay, so I'm going to use the same scenario for both sides, balanced and unbalanced or net, because I want to make sure you see what actually is the difference between the two. Now, one of the words that we got to remember here is that word vector that we learned last Thursday. All right, actually we learned it last Wednesday, a vector. All right, does anybody remember what a vector was? I know it was last week and some of you had a good weekend, but does anybody remember what a vector was? It's also a vocabulary word. All right, Jordan, what's up?
A quantity that has a magnitude and a direction.
Okay, quantity that has a magnitude and a direction. All right, so what did that mean when we were talking about that last week? Does anybody remember? Nobody remembers what that meant? So must quiz more often. Gotcha. All right, so what that means is when we talked about displacement, we said that you could be 5 meters, right? 5 meters away from where you started. That's a measurement. But a vector, what makes it a vector is when you tell me I'm 5 meters east or I'm 5 meters west, because now you've given me a distance and you've given me a direction, and so that's what makes it a vector. All right, and so in this case here, we're going to have to remember about vectors, but now here's this scenario we got going on here, okay? So right here, I've got somebody who's going to be pushing on that box. All right, so I've drawn somebody who's pushing the box. They're trying to move the box. Everybody see that diagram? All right, it's a stick man, so you can't say I can't draw. I literally just drew a stick man. All right, everybody can draw a stick man. It's just called lines. Okay, they don't even have to be straight. Now, he's going to be pushing on that box. All right, he's going to be pushing on that box. So now he's going to push on that box. All right, with a force of, let's say, 5 newtons, which now I'm teaching you a new unit. All right, the unit for force is newtons. Okay, the unit for force is newtons. Be thinking of what was the unit for distance, for velocity, and for time. Be thinking of those again. Mr. Simon. Hey. All right. Mm-hmm. So balanced force, right? Now, force we measure in newtons. What do we measure velocity in? Close. You said miles over seconds. No. We don't. Meters over seconds. All right, meters. Okay, not miles. Meters over seconds, right? What about acceleration? Meters over seconds squared, right? What about mass? Grams, right? All right, so I'm just trying to make sure you guys start thinking about these units again. So we have a guy pushing this way, right? But now, for this to be balanced, we said that another word for balance was going to be what? Equal, right? Well, right now, if I only have one number, I can't say it's equal, because that's equal to what? So what that means here is, in the case here, on the other side, we're going to draw somebody else who's also pushing. Okay? So that person now is pushing, but what do you notice about their push? Which way is he pushing?
The other way.
He's pushing the other way. All right? So if we look, we can see that their pushes are in opposite directions. Does everybody see that? So this is that competition that I say is always happening in nature. This versus that. All right? Here we see that person A is pushing to the right. He is applying a force to the right, while this person over here is applying a force to the left. All right? Now, because this is balanced, we know that this guy is applying a 5 Newton force also. So the force that the guy on the left is pushing with is the same amount of force that the guy on the right is pushing with. So if they each are pushing the box with the same amount of force, then what do you think is going to happen in this situation?
It's going to be balanced. The box is going to stay.
The what?
The box is going to not move. It's going to stay in the same position.
Okay, and that's the important part, because remember, what this unit is called motion and forces. And so what we see here is this. Because we have two forces that are being applied onto that box, one to the right and one going to the left, but because those forces are of the same amount, equal magnitude, then what happens here is the box does not move. And that's the main idea. That's the big idea that you have to remember about balanced forces. When the forces are equal, that means nothing is going to move. That means the box stays put. All right? I could even do it where if I change the scenario, right here, let's say that they were pulling on the box, right? Let's say there was a handle on the box and they're each trying to pull the box toward their own side. Well, if I'm pulling with a force of 5 newtons and the other guy's pulling away from me at a force of 5 newtons, well, again, it's like a tug of war, right? If you have equal teams on opposite ends of the rope, where does the rope go? Nowhere. Okay, that's what makes that scenario kind of dull. If you're watching the tug of war, if both teams are equally strong, then the rope never moves, no team ever wins, and you just see two people pulling on a rope that doesn't go anywhere. Okay, what makes the game a whole lot more interesting is when the teams are not equal. Okay, they are not balanced, and so then what happens here is you have on this side of the box, you have somebody who is pushing the box. But then again, over here, you have somebody who is pushing the box. Okay? And because both of those people are pushing the box or pulling, it doesn't matter. Okay? Matter of fact, maybe I should even do it where the arrows go in the opposite direction, but their body posture would not make sense. So let's say this. We know he's pushing that way. And we know he's pushing that way. Okay? Because they are unbalanced forces, what do I know about the numbers that are going to go above the arrows?
They're not going to be equal.
Okay? They're not going to be equal. So let's just do this real quick. All right? Ms. Holmes, give me a number to write above the left arrow. 7? Okay. All right. And let's see if Jayla's paying attention. So Jayla, since this is going to be a force, what unit should I put after the 7? N. All right. Which stands for what? Newtons. Okay. Why do they call it a Newton? Anybody know?
Newton's first law.
I mean, you could say Newton's second law, Newton's third law, right? Why do they call the laws Newton? Who's it named after?
The what?
The what? The word Newton?
No, what did you just say?
Who is it named after? Anybody? Isaac Newton. Okay. Does anybody know anything about Isaac Newton?
He's a scientist.
You know what he is a scientist of? Do you know a story about Isaac Newton?
No, ask me.
Oh, well, I asked first. Okay. Anybody know anything about Isaac Newton? Hold on, say it again. Something about apple, Alondra. Go ahead. What you got?
Didn't he get hit with an apple on the head, like an apple fell from a tree, and then he wondered why?
Correct. Right. He got hit in the head with the apple. Right. That's the story with him. Is he was sitting under an apple tree. Apple fell, hit his head. What idea came to him from that?
Apple fall.
Well, that was the question, right? But that led to this idea. What was the idea? Gravity. Okay. I mean, gravity. So, the idea of gravity is, conceived by Sir Isaac Newton. Now, remember, that's a law, right? The difference between a law and a theory is that a law, you really don't have there's no way you can test. You know what I'm saying? How we talked about, do these jeans make my butt look big? Right? You can test that out because you can try on jeans and see if it makes your butt look big, right? That's why that would be called a theory. When you have evidence to explain something, that's called a theory. When you just have a law just simply explains, it just kind of, you always knew it, you just put it into words. All right? And so, but Newton was the one that came along with the law of gravity, helped put that in perspective, all right? Which again, is important because gravity is a force. All right, gravity is a force. So that's why we name forces after Newton. So because he was the first one that came along with the force. So we're talking about unbalanced forces. Okay, we're talking about unbalanced forces. So here's my question now. Right, we know that the guy on the left is applying a force to the right. He's pushing that way with a force of 7 newtons. Okay, for this to be unbalanced, Nigel, what does the guy on this side have to push with? Okay. 4. All right. So he says less. All right. And he said 4 newtons. Would that be unbalanced? Yes. Does it have to be less? No, it could have been more, right? Because I could have put 9. Would that be unbalanced? Whatever number it was that would not be equal to 7. Right? So, but he chose 4, so I'm going to stay with his number. So we got 4 newtons. Okay? So notice, on the left side, did we have a winner? No. What happened to the box? Stayed the same. Okay, it didn't move. When we say stayed the same, meaning it stayed in the same spot. Didn't move. Okay? On the right side, are we going to have a winner? Yes. Who's the winner? The one on the left, right? So now my question here is this, and now here's where very, 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 very important. Like here's where you got to pay attention to what the story was. Okay? So who is the winner? The one on the, which means the box is going to move to the right. But it's going to move to the right because what kind of force was he applying? A push or a pull? A push. Okay? That's why it's going to the right. So right here, I'm just going to write underneath, box moves right. Okay? So we know here, because they're unbalanced, we know the box is going to move. But the second thing you got to know is, well, which way is it going to move? Because that's what they want to know. They want to know when you have forces, when does a box move? All right? And then when a box does move, how do you know which way it's going to move? But now what I'm going to do here is I'm going to throw you another diagram underneath this one. Here's one that I've really never drawn before, so this may look ridiculous. All right? So I'm going to just do it like this. He's got long arms. Okay? So here, all right, we're seeing that they're pulling on each end of the box, right? And again, what kind of forces are these? Well, what kind of forces are these?
Unbalanced.
Unbalanced, right? But remember though, we're not going to really see the word unbalanced, right? So what's the word we got to get used to? Net forces, okay? So in this scenario here, Machala, give me a force for the left side. 10. 10 what?
Means.
10 what?
Ends.
10 ends. What does the N stand for?
Next.
You just say next?
Next. Next.
No. Scientist.
What?
Scientist.
His name.
Yeah, his name.
I don't remember.
You don't remember his name? Sitting on the tree, the apple fell on him? No? Sometimes have a little snack called a fig?
The what?
Never mind. All right, Newton. It's called a Newton. 10 newtons. Okay. A devil. This is going to be unbalanced forces, right? So give me a number for the right side.
3.
3? Okay. How about this? Let me do 13. That way we got one where it's bigger on the right side, right? Okay. I'm going to go 13. 13 newtons. So, are they equal? No. Who's the winner?
The right.
The right side, correct? So in this scenario here, which way is the box going to move?
Right.
Okay? Because the greater force is on the right side, the box is going to move to the right side. Why? Because here, right, they were pulling. Here, they were pushing. So just kind of pay attention to that fact. You know what I'm saying? Like, don't just start looking at the scenario and say, well, in the diagram he gave us, you know, the bigger number was on the left side, so the box moved to the right. Okay, well, look at the bottom diagram. The bigger number's on the right side, and the box still moved to the right. You know, so you got to pay attention to the context. Am I pushing or am I pulling? That's important for you to know, because remember, a force is a push or a pull. All right? So that is your balanced and unbalanced forces. Does anybody have any questions about that right there? All right, there are different kinds of forces. Like I said, the two main forces you want to know about right now are simply gravity. Well, three. Gravity, which causes things to go in which direction? Down. And then you have friction, which causes things to do what? Stop or slow down, right? And then the other force you have is just the one that you apply, you know, like whenever you shove something or whenever you pull something, right? So again, right now you guys are applying a force onto your pencil. That's why your pencil moves. All right? If you did not apply a force onto your pencil would not move. Now, here is the good news and the bad news. Here is the formula we got to learn for today. All right? But there are two of them. Okay? There are two of them. And they can be confusing if you don't pay attention to when you're supposed to use them. So again, what I'm going to do is I'm going to do a side by side so that you can see the difference between the two. All right? However, I need to get another marker because this one, once my markers get harder to erase, then it's fading. Where are my markers? Here are my markers. All right. All right, so F equals MA. That's the formula. All right. Then we're going to draw a line. Uh-oh, this marker's getting ready to die. This is a brand new marker. F little g equals mg. Okay. Now, I'm going to put to the side, you know what I mean, what we call these here, because this right here, this is the one that I call the force formula. All right. And the reason why is because this is straight up force. Like, I don't care, you know, if I punch you, I apply the force. If I move you, I apply the force. Okay. If I drag you, I apply the force. That's the force that I'm talking about. Okay. But over here, this force is a force that involves gravity. Okay. And what did we say gravity causes things to do? To fall or drop, right? So I'm going to just put right over here, gravity equals fall, okay? And so the reason why we have two different formulas is because if gravity, like sometimes, like I could punch you hard or I could punch you lightly. So in that scenario, the forces may not be the same. But when something falls because of gravity, they're going to fall consistently. So therefore, we have to have a formula where you have that component where gravity is involved, where you know that everything's going to have a consistency to it. All right? Well, when gravity is involved, we call that force weight. Okay? We call that force weight. So now, I want to make sure, here's where I got to make sure we don't get things confused. All right? So we're going to draw, not a draw, sorry. We're just going to write over here. All right? I'm going to put a little star, and we're going to make sure we understand the difference between mass and weight. Okay? And I got a very easy way for you to understand it. Okay? I got a very easy way for you to understand it. Remember we said mass back in the second week, or the, whatever you call it, third day of the semester, when we were talking about the SI units and we had mass? How much material, right? Okay? So that's why I want to make sure you remember. I want to make sure you remember this. It is mass is material. Weight is the effect of gravity on that material. Okay? Mass is measured in grams. Weight is measured in newtons. Now some of you would say, I thought it was measured in pounds. It is in the English system. Okay? Just like in the English system, we measure distance in miles, right? But in the SI system, we measure that in kilometers. Well, in the SI system, we measure weight in newtons. Where in the English system, we measure weight in pounds. Okay? Now, newtons is usually kind of like, if you kind of wanted to gauge a realm, a newton is like half of what a pound is. So like if somebody were 75 newtons, they would probably be about 150 pounds. So just kind of giving you a gauge. All right? That's a rough estimate though. Now, here's the issue. on the moon. Okay? So I want to make sure we kind of get this thing straightened up on the moon. Okay? On the moon. When we deal with something like this, all right? On the moon, if you are, let's say this, I'm gonna draw a person. This person is 75 kilograms. Okay? That person is 75 kilograms. Well, there's no difference between mass on the moon and mass on the earth. Okay? That person on the earth would still be 75 kilograms. All right? Meaning, if I go to the moon, like right now, I'm fat. I take up a whole lot of space. I am made of a lot of material. Okay? If I go to the moon, guess what? I'm still fat. I'm still taking up a lot of space. I'm still made up of a lot of material. Because my mass or my material won't change here compared to on the moon. Because, the material is what it is. All right? However, since weight is the effect of gravity on material, well then, if the gravity changes, then my weight can change. So, I may be 75 kilograms on the moon, just as I am 75 kilograms on the earth, but let's just say this though. If on the earth I am 180 pounds, okay? If on the earth I am 180 pounds, well, the moon, when you're in space, do you have more gravity or less gravity? Less gravity. That's why people do what? They float, right? So on the moon, I may be 2 pounds. So you notice how the numbers change? The number changes for weight, but it doesn't change for mass. Because mass is the material. Weight is the effect of gravity on the material. The material ain't going to change, but the gravity's effect on it can change. All right, that's kind of what we're talking about there. Just like, we'll use it in a scenario of if you buy a polo shirt, right? If you buy a polo shirt at Walmart, it might cost you $7.97. Okay? But if I stick a brand on that same polo shirt and put it in another store, even though it's the same material, same amount of material, same color material, because I put a brand on it and put it in another store, now it might cost you like $75.97. You know what I mean? So that's kind of the same idea. The effect of gravity is like the effect of a brand. The brand can change the value. But mass is the material. It ain't going to change what it's made of. All right? It's still made of the same stuff. Now, let's get back to over here now. So now that we kind of have an explanation, let me take my time on this one. All right? First of all, if you suck at algebra, there is a triangle. All right? This triangle looks like that. Okay? F is at the top of the triangle. Okay? M is in the bottom left corner. A is in the bottom right corner. And then we got to list our variables. All right? F stands for force. And, Machala, what do we measure force in?
Newtons.
Newtons. There you go. Okay? Newtons. Apparently you've never eaten a fig Newton before. Never eaten a fig Newton before?
What is it?
Never mind. That means you have not eaten a fig Newton before. Okay? All right. M stands for what?
Mass.
Mass. Okay? Now you ready? Here's where you have to be careful. Okay? This is where we get into those, why does this got to do this? You all right? And the only answer for me is just because they want to make your life miserable. All right? But this is the truth. Mass in this scenario, we said mass is measured in what? Grams. But now for force, it has to be kilograms. All right? It has to be kilograms. So let me be that one person. Mr. Science. All right, so what happens if they give you 500 grams? Then you got to convert it to kilograms. I don't know how to do that. Yes, you do. It's called what? King Henry died by drinking chocolate milk. Okay? That's how you convert it. All right. So that's why we learned that in that test 1, because I knew you're going to have to come back and use it on test 2, and then you're going to use it again on test 3. All right. So that's why I need you to make sure we understand. Like, you might want to do something, put a little highlight or something. Just realize you can't just accept grams. It's got to be converted to kilograms. Now, if I'm nice, or if the problem's nice, it's already in kilograms, right? So that's something you got to pay attention to. So don't just sit there and say, oh, there's the mass, and go ahead and convert it. What if it's already in kilograms? Then you don't got to do anything. If it's in grams, you got to do something. So you better look and see, do I got to find the mass, and then say, do I need to do something? All right? Because if it's in kilograms, you don't. A stands for what?
Acceleration.
Acceleration. It's almost as if he's looking at his reference sheet. But he's probably not. He just happens to know this stuff. But it is on your reference sheet. Acceleration is measured in what unit?
Meters over 6.
Whoa. What? What did? I don't know what she just said. I don't want her to repeat that, though. Meters over second squared. All right. Oh, I think I know what she said. You say M over S?
Yeah.
Oh, okay. Sorry. I don't know what you just. I thought you said something else. So acceleration is meters over seconds squared, right? Remember the other way that they might write it is m/s/s, correct? I said that the other day. All right. There's that right there. Are we good with force?
Yes.
Okay. Let me give you some tidbits here, okay? If it involves throwing, punching, hitting, okay? You want to use that formula there. All right? If I shove somebody into a door, that's the formula I'm using. Okay?
Wouldn't throwing be on the other side?
Depends on how I'm throwing. That's why I say when I throw a baseball, that is force equals MA. Okay? Now, if something over here involves, well, first of all, FG, right, stands for weight. It is a force, so it is measured in newtons. M is what it always is, mass, but it's got to be in kilograms. Okay? And then G, the good news is acceleration. It is the acceleration due to gravity. G will always be 9.8 meters per second squared. It will always be 9.8 meters per second squared. So, if you recall, you remember last Thursday when we did that velocity problem, about somebody was driving and they hit into the side of a building, right? And I said, well, what was the VF? And y'all were smart, and you all said the VF would be 0. I said, but there is no 0 up there. You said, but I know, but it stopped. Well, that's going to be the same thing here with this particular formula. When you're using this formula here, you may only get one number in the problem. The number is either going to be the force or the mass. Because if you're using this formula, this number is automatically set. It won't be in the problem because it's in the formula. All right, so if you look at your reference sheet, you see the formula F little g equals mg. In the middle, you see where it says g equals, and it says acceleration due to gravity. And then if you keep reading, it tells you 9.8. You don't have to memorize the number because it's on the reference sheet, but you got to memorize the fact that it's on the reference sheet. Like, you got to remember that there is a number there. You don't have to remember what that number is because you can then look it up. But if you forget to look it up, then you're going to be kind of hurting a little bit when you're trying to do these problems. All right? On this right here, the word you're looking for here is this. If something is lifting or falling or dropping, then you got to use force weight. Because again, why is it falling? Because of gravity. Why is it dropping? Because of gravity. All right? Lifting, you would say, well, that doesn't involve gravity. Yeah, but it actually involves you to go against gravity. That's why, again, if I'm walking up a hill, it's a whole lot more work than if I'm walking down a hill. Because if I'm walking up a hill, I'm going against gravity. But if I'm walking down the hill, gravity is my friend. It's helping me out. Okay? So that's why sometimes you got to pay attention. You would still use the force weight formula if you're having to go up, like lifting, because that goes against the law of gravity. All right? So here's all your information for forces, all right, and then force weight. Okay? So what we want to do right now is I want to show you, by the way, there is a triangle here. in case you haven't figured it out, and some of you don't tend to figure things out very well. All right, so there's your triangle, should you need that triangle. Okay. Remember, if you're good at algebra, you don't need triangles. Okay. But if you're terrible at algebra, then that's why you do need the triangle. All right. So, with that in mind, let me give you a sample one that I want you to look at to make sure that you are good. Now, obviously, for this problem to get up on the board, you are going to need. There we go. I'm gonna need my board. So, can I erase? Everybody's good? Machala? I'm good to erase?
Yeah.
All right. Victor, if you would turn on that button on that projector, I would be most appreciative. It's got a lot of information there, guys. So again, things that you got to remember. Force is measured in newtons. There are two formulas for force. How do I know which one to use? You have to read the story. If it involves gravity in any way, then you use the force-weight formula. If it doesn't involve gravity, then you don't use the force-weight one. You just use the straight-up force one. All right? So, let me slide that stuff over. It's okay if it's angled. It won't hurt your feelings. All right. So it says here, an object of mass 300 kilograms is observed to accelerate at the rate of 4 meters per second squared. Calculate the force required to produce this acceleration. So if I want an object that has a mass of 300 kilograms to accelerate, which means to pick up speed at a rate of 4 meters per second squared, well then how much force do I need to shove it with, I guess you would say. How much force do I need to push it with, right? So again, what's the first thing I tell you to do in a word problem? Not look at the numbers yet. Okay, look at the question first so that you can then, Alondra, figure out what formula you want to use, right? So what is the question asking you to find? What does the question specifically say? Calculate the force. So what am I looking for? Force, right? So now, before you go there and you just plug in your force equals MA, my question here is this. How do you know it's force equals MA and not FG equals MG? See my point there? You can't jump the gun. Well, it said force. I know, but weight is a force. So you could either use F equals MA or you could use FG equals MG. So which one do you think you're supposed to use here based on what you read? Okay, F equals MA. All right, Medeva, why? Because it says acceleration. All right. All right. And that's, I would say, not a good enough reason to back up your claim. Okay. What's another? Why else might you suspect that you would use F equals MA?
Because you're not lifting or dropping.
Right. Do you see the word fall in the question? Do you see the word drop in the question? Is there anything that indicates that this thing is going to be going down? No. So if there's no indication that it's going to be going down, then your safest bet is to then just say, let me use force like normal. All right? So I'm going to use my force formula is going to be F equals MA. All right? Then I'm going to list my variables. And so therefore, when you get to the listing of the variables part, that's where you go into the problem, and then you start circling whatever numbers you come across. Remember, the circling thing works as long as you can identify it. But if you go over there and you circle 30M and you don't even know what M measures, then circling ain't going to do anything good for you. All right, so as you are beginning to fill in your variables, let me see what some of you are getting in for your variables. And if I call on you and you haven't done that part yet, then there's no better time than now to do it now. So don't ignore it thinking, oh, if he calls on me, I'll just say I don't know. Then I'll make you tell me then. Because we got to start learning this stuff now. All right? I mean, right now, you have 3 formulas that you're responsible for. Now you're getting formula 4 and formula number 5. Tomorrow you'll get formula 6. Okay? Because we had density on the last test. We got velocity on this test. Acceleration on this test. Force, weight, right? And then we got tomorrow we'll get momentum. So that'll be 5 on this test, but 6 total. All right. Deshanti, F equals, what did you put? You put an X? All right. So she's putting an X. Okay. Why'd you put an X? You don't know why you put an X? You just figure it's the first thing I got to put an X? Okay. That's probably not the best thing to do from now on. So let's figure out let's kind of figure it so that you know why you're putting an X there. All right. What does the F stand for? Force. Okay. What did the question specifically say in the word problem? Calculate the force. So what are we looking for? The force. So that's why we put an X. All right. Not because F was the first one listed. All right. But because we're looking for the force. All right. So, Nigel, what are we putting for M equals? 300. 300 what? Kilograms? Because here's my question. Holmes, do I got to convert that mass? Huh? No? You sure? You're not really sure? Okay. In our notes, you feel free to look at your notes. What did I say your mass had to be in? Kilograms? Is it in kilograms? So do we need to convert it? Now you sure? All right. So you see what I'm saying? Like you could talk yourself out of something if you're not paying attention to what your notes say. Like trust your notes because I'm the one that gave them to you.
Hold on.
All right. I'm holding.
When we converted it, what we start with the M?
No. It depends. Like let's just say this. Let's say the problem had given you 300 grams, right?
Yeah.
So then you'd have to convert 300 grams into kilograms. So what would you start with?
The U.
Correct. And so where on your thing would you start?
The base.
Good job. Where would you go?
To the K.
To the K. So you're going left or right?
The middle.
Left. How many spots?
To the beginning.
How many? How many spots is it from the B to the K?
I guess 5.
You get 5 or 4? Okay, so you ain't written it down yet. You were actually impressing me for a while. All right, but you're absolutely right. Everything you said is right. All right, except for how many spaces. You moved 3 to the left. All right. Now, good question. Ready? Here's another question for you there, Machala. There's my number. Where's the decimal right now?
Behind the 0.
Behind the what?
Behind the 0.
Which 0? There's 2.
The last one.
The last one. Okay, good. Just making sure. Didn't want you to start in the wrong spot. A equals there. Victor, where are we going to put there?
4 meters per second. I mean, the 4 thing.
4.
Meters over seconds squared.
There you go. All right. 4 meters over second squared. Okay. Medevil, according to our formula and whatnot, right, or the triangle, whichever one you need, what am I going to do with those 2 numbers? You're going to multiply? You sure? All right. And so when you do multiply them together, Barney, what do you get? Newtons. All right. So you get 1,200 newtons. And I'm good. Okay. I don't worry about significance. However, if you wanted to get that bonus point, right, what would your answer be in significance?
1 point.
Nope. Say what? No. Huh? What? It'd be just 1,000. Because you remember, you got 1 significant, you got 1 significant, right? This has got 2 significant, so there's my first. That means that 1 stays 1, and then I fill in that 2 with a 0, 1,000.
We don't divide.
Don't worry about significance. That's gonna ruin your weave. All right. So, what we got here is we got force. Yeah. No. Remember, significance is only a bonus thing. All right. So right now, if you go and hold on, what was that again? I would just say forget about significance. All right. Either you can right now or don't worry about it. There's your question. There's your answer for that one. Everybody's got them in the notes, so we're good? Okay? All right. Let me show you what one looks like that would be a gravity-based question. A gravity-based question. There you go. It ain't much. Okay? But I can guarantee you this. If you went through the process, here's what you're going to do. Here's what some of you would do that don't pay attention to what you're doing. You'd come over here and you'd say, all right, do here, here, all right, and then you'd go X, 60, and you say, hold on, I don't see any number. Then you call me over, Mr. Science. Like, I don't know what to do. And I'd say, well, read the question. I did read the question. Okay, well, read it again and pay attention to what they're asking you to find. I mean, that's the formula, right? That's what you would do. When you get to a point right here where you're like, there's no other numbers, that's where you should be, something should be triggering that brain of yours to say, hold on, then maybe this is that one where the number's already set in stone. Okay? And because, again, the word here is weight, which means I'm using F little g equals mg. So F little g is my weight. That I don't know, because that's what the question told me to find. My mass is 60 kilograms. Alondra, do I need to convert that 60? All right. And then my g would be what? 9.8 meters over second squared. Well, now I got numbers for me to do something with. Where up here, I had nothing to do. All right. Down here, I got something to do. The only difference is this formula, you would not look at the g. Down here in this formula, you look at the g and you see there is a number already set in stone. So that's kind of what I just want to make sure you realize. All right? Yes?
When you use the unit force, you gotta put the G with the Newton.
Hold on one second. This concludes the recording of